Hey, welcome to the Explainer. You know, our entire world runs on a set of invisible rules. The laws of electricity and magnetism. We're about to crack the code on what they are, how they work, and most importantly, why they matter. So let's jump right in. So let's start with a question that sounds like a bit of a riddle. What on earth could a deep space probe, one of the most complex things humanity has ever built, possibly have in common with a simple magnet you'd stick on your fridge? The answer is actually pretty amazing. And that's the secret sauce. All of our mind-blowing technology, from the simplest gadget to a spacecraft exploring Jupiter, is built on just a few core principles. These rules are everywhere, they're predictable, and once you get them, you start to see the world in a whole new way. And the way we're going to do this is, I think, really cool. We've grabbed a bunch of questions from a real electrician's certification exam. So each question is going to be like a key that unlocks one of these huge ideas. It's basically an inside look at the practical knowledge that literally keeps the lights on. All right, to get started, we need to dive into the most familiar of these invisible forces, one that can feel like straight-up magic, but is all pure physics. Yeah, I'm talking about magnetism. It's one of the fundamental forces of nature, and as you're about to see, it is deeply, deeply connected to electricity. Okay, so here's our first question from the exam. It seems simple, right? But it gets right to the heart of how magnets actually work. You'd think, maybe, that heat is energy, so it should make the magnet stronger. Well, the reality is the complete opposite. So, we know the basics, right? North Pole, South Pole, invisible field lines. But look at that last point. Heat is just chaos at an atomic level. It makes all the tiny atoms vibrate like crazy. For a magnet to work, all its little magnetic parts need to be lined up perfectly. Heat messes up that perfect alignment, and so the magnet gets weaker. Great question, and it's one that every electrician absolutely has to know. This takes us from just knowing that magnetic fields exist to understanding their shape and their direction, especially when an electric current gets involved. An answer is this awesome little trick called Ampere's right-hand rule. Seriously, think of it as the secret handshake between electricity and magnetism. It's a super simple way to visualize a force you can't even see. You can do this right now. Seriously, imagine a wire, and the current is flowing forward, away from you. Point your thumb in that same direction. Now, just curl your fingers naturally. See the direction they're curling? That is the exact direction of the magnetic field wrapping around that wire. It's that simple. And this just brilliantly shows us the biggest takeaway here. This is not a sometimes thing. It's a law of the universe. An electric current always creates a magnetic field. They are two sides of the exact same coin. This is the very heart of electromagnetism. Okay, so electricity makes magnetism, but can we go the other way? Let's see how we can actually harness other forces to create and control electrical energy. All right, here's our next exam question, and it sounds more like a chemistry experiment, but the result is pure electricity. So picture this. You take two different kinds of metal wire, you twist them together to make a loop, and then you just heat up one of the spots where they're joined. What happens? This wild phenomenon is called the Seebeck effect. That temperature difference, it creates a voltage, and that voltage pushes electrons, creating a steady electric current. You are literally turning heat directly into electricity. No moving parts, no generators, nothing. Just heat and current flows. And hey, remember that deep space probe from our very first question? This is it. This is the answer. Probes like Voyager are so far from the sun that solar panels are useless. So they carry a little block of radioactive material that gets hot all by itself. And they use the Seebeck effect to turn that heat into all the electricity they need to explore the solar system. How cool is that? Okay, so we've seen how heat can create electricity. But let's flip that around, because you experience the reverse every single day. You know that little bit of warmth you feel from your laptop's power brick or your phone charger? That's not an accident. It's a predictable effect of electricity. It's all explained by something called Joule's law. Now, don't let the formula on screen freak you out. It's actually super simple. The heat, H, is just based on the current, I, flowing through the wire's resistance, or R, over a certain amount of time, T. Basically, the more current you push through a wire and the more that wire resists it, the hotter it's going to get. That warm charger? Yep, that's just Joule's law in action. So we can create a current. We know it generates heat, but how do we actually control it? How can we store its energy and use it when we need it? Well, for that, you need some special components designed to tame that flow.
And that brings us to our next exam question, which is all about a component called an inductor. This property is called inductance. And honestly, the best way to think about it is as electrical inertia. As current flows through the coil, it builds up that magnetic field, and it's actually storing energy right there in the field. The stored energy then pushes back against any change, smoothing out the flow of power. It's like a flywheel for electricity. All right, we're in the home stretch. We've seen the forces, we've seen the components that contain them. Now for our final act. Let's look at how electricians actually arrange these things to build the massive high-power systems that run our cities.
See, when you're dealing with really heavy-duty power, like for huge industrial motors or sending electricity across the country, you use something called three-phase power. You can think of it as three synchronized electrical signals, all working together for more stable, efficient power. But you have to wire it up just right. Our final exam question looks at the two most common ways to do it. They're called delta and Y connections, pretty much because of the shapes they make. The delta connection, the triangle one, is a beast. It's great for high power, and it's super reliable. The Y or star connection is more versatile because it gives you a handy neutral point. But what's really key for an engineer is knowing that these two are directly related, and you can use that little conversion formula to switch between them when you're designing a big, complex power grid. And that brings us to the end. You know, Joule's law, Ampere's rule, the Seebeck effect, these aren't some new discoveries. These ideas are the 19th century foundations that our entire 21st century world is built on. It just makes you wonder, right? What elegant, invisible laws are we on the cusp of discovering today that will be powering the world 150 years from now? Thanks for watching.